Good afternoon, everybody. Welcome again to the seminar series of the EC department. So today, I'm pleased to have Dr. Julio Romero Agüero present about power system resilience in the seminar series. So yeah, he will introduce himself in more detail, but a short biography of him is that Dr. Agüero is the Vice President of Strategy and Business Innovation at Quanta Technology. He has over 25 years of experience providing leadership in quantum technology in the areas of technology and business strategy, innovation, grid modernization, distribution system planning, reliability, resilience, and integration of distributed energy resources. Dr. Agüero currently is a senior member of IEEE and serves as Vice President of Membership and Image in the IEEE PES Governing Board. He has in the past served as the chair of IEEE Distribution Subcommittee, IEEE Working Group on Distributed Energy Resources, and he has served an editor of multiple journals. Most recently, he was also chair of the IEEE Innovative Smart Grid Technologies Conference in DC in the past 2 years. He's also adjunct professor at University of North Carolina, Charlotte. So please join me, welcome him, and Julio, we can't wait to hear from you. Thank you for joining us.
Oh, thank you. Thank you so much, Masood. Good afternoon, everyone. Again, I just want to thank Professor Parvania for the invitation. He and I serve in the organizing committee of ISGT North America. So we have been working together for a few years, and it's been a pleasure to work with him. So thank you again for this invitation, and I look forward to interacting with you all and listening to your comments and any questions you may have. So I was mentioning that, well, I have I don't remember exactly, but I have a lot of slides, probably more than the ones that I can cover in this presentation this afternoon. But the intention today, this is going to be more of an introductory conversation on some of the things that the industry, the electric power industry, especially in North America, is focusing on in this area of resilience. Although the discussion is going to be on resilience in power systems as a whole, the main focus is going to be distribution, applications to distribution, which is my area of expertise. So at the beginning, we'll talk about concepts that apply to the entire power system, but then we'll focus on some of the applications and solutions that are more related with distribution systems. So before we start, I want to spend a few minutes. Professor Parvania asked me to share a little bit of my experience and some advice on a career path or a career development in the power industry. So I'll share a little bit of my experience. This is my perspective, and you may agree or disagree with it. It's just basically a little bit based on my experience working. I have been working in this industry for the last 25 years, and especially the last 10 years, I have noticed a significant change. There is an ongoing evolution that is so exciting. I haven't seen it before. So there are so many opportunities nowadays for all of you to explore and to working in really exciting areas like renewables or cybersecurity or advanced planning, or what we are going to discuss today, resilience, reliability, automation. There are so many things that are so exciting. So my perspective, of course, is from an industry point of view. You have Professor Parvania and others who can share their perspective on an academia path. If you want to become a professor, or if you want to work in academia, or I would say even in a research organization, in national lab, probably I would say definitely Professor Parvania and others are more qualified to advise you. But on the industry, from the industry point of view, generally what I have observed is usually you end up pursuing one or one of two paths. Generally, there is a technical leadership type of path in which you become a technical expert. You may become an individual contributor, somebody who is well recognized in the industry as, okay, this person is the top industry expert or one of the top industry experts in a specific area. It can be protection, it can be, let's see, planning, it can be distributed resources, etc. It's a very exciting path, but the type of skills are more related with technical expertise. And in some cases, a technical leader can have a team that works with that person, and let's see, and this person provides that type of leadership or guidance to a team. There is another path that is more related with business or with managing a business, and that is typically people call it a manager path. And this is the path that usually executives follow. And eventually they may become, for instance, a vice president or an executive, a CEO in an organization. And the skill set is different. It requires a lot of soft skills, interaction with people, the ability to manage groups, manage teams, the ability to develop business, the ability to market products and services and solutions. So it's a different type of skill set, although I would say that even in that career path, you need to have command of the specific subject matter. So you may not be a technical expert, but you know enough about a subject to communicate well and to have conversations with decision makers and even with technical experts. Now, generally, as I mentioned before, when you join the industry, and what I mean by the industry, I mean, for instance, electric utilities, consulting firms, vendors, manufacturers, etc. But generally, when you join the industry, the first few years, you're trying to define who you want to be. Do you want to become a technical expert? Do you want to become a business leader? And it takes some time. It may take you, a few years, 5 years or so. And it's a good idea to try different things during that beginning of your career. So you get to experience different things and then select what you think that is where your passion is. Sometimes folks want to be both. They say, hey, do I have to be one or the other? Can I be both? And the short answer is yes, you can be both. It's doable. It's difficult because if you become, for instance, a business leader, that is going to absorb the majority of your time, and you may not have enough time to work on projects, for instance, that require a lot of technical expertise, because that also requires time. So it is doable, but it's difficult. It requires a lot of commitment from you. And I know some people who have been able to accomplish it. Folks who, for instance, are the CEOs of a company and they lead large organizations, but at the same time, they are also, for instance, members of the National Academy of Engineering. They are technical experts for sure. So my suggestion when you begin your career, try to explore different options. Try to learn from each one of them, and then eventually focus on that, on identifying your passion. Because if you identify it, then you're going to enjoy. You'll not be working. You'll be having a lot of fun if you select the right area. Regarding your career plan, something that is very important is that you need to write it. You may have these ideas about what you want to be, what you want to become in the future, but it's a good idea to have a kind of equivalent to a resume. This is your career plan, and it's dynamic, and you're going to update it periodically, but you have a list of things that a list of things that you want to accomplish. What do you want to be? Where do you want to be in 5 years? What do you want to learn? What are your goals, your objectives? What do you want to accomplish? And 5 years is usually a good starting point. Once you, after 1 year, you can update it. You usually at the beginning of every year, you try to update it, try to summarize what you have accomplished so far, and then try to include feedback and update the plan, and it becomes dynamic, but eventually it's going to take you there. Something that is important about that plan is set goals that are realistic. You need to be realistic, but at the same time, it's a good idea to include some stretch goals. So it's good to dream a little bit, let me put it that way. So you have something that motivates you, and try to achieve your stretch goals. If you aim at your stretch goals, for sure you'll accomplish your realistic goals as well. And again, develop that plan, try to accomplish it. And a good idea at the beginning of your career is to try to find a mentor. A mentor is generally somebody who is a senior, somebody you look up to, and somebody who can provide guidance and advice. It's a good idea that that person is not your boss or your boss's boss, not somebody you report to, but somebody who can provide a more impartial or objective perspective on your career. So that's one thing. One thing is to have a mentor. A different thing is to have a sponsor. It's a good idea to have a sponsor as well. Sometimes your mentor only provides guidance. A sponsor is somebody who also gives you opportunities for growing. And usually, a sponsor is it may be related to you hierarchically. It may be, as I mentioned before, maybe your boss's boss or somebody in the hierarchy of the organization you're working on. Or it may be somebody who, for instance, who is involved in industry activities like IEEE, who can give you opportunities to participate in IEEE activities. But somebody who help you grow. Your mentor sometimes is also your sponsor, and that is a great combination, but not necessarily. They are not necessarily the same all the time. And to finalize this initial part of the conversation, what I wanted to say is also that, well, the industry is changing a lot, as I mentioned before. The required skills today and tomorrow are going to be different, are certainly different than the ones that were required 10 or 20 years ago. Something that I have noticed in my experience is, especially when you're doing, when you're getting your advanced degree, a Ph.D. or a master's degree, many of you are in that stage of your career, you tend to focus a lot on intellectual capabilities and your training, and that is certainly valid. I mean, that's the reason why you are doing your advanced degree, getting your advanced degree, because you want to learn more. So you're very proud of those that additional knowledge and your intellectual capabilities, because it's not easy to get an advanced degree in a field like ours, in electrical engineering. It's not easy, and you have to work hard and you have to be smart. But once you join the industry, once you start working, you realize that that's, I would say, that's the baseline. That is almost like a given. That is something that is expected from you. You finish your advanced degree. We know, if we hire you, we know that you're smart. We know that you know about the field. But there are other things that are equally, and if not more important, sometimes. And those are related, again, to soft skills, to leadership, to being a good team player, getting along with people, getting along with clients, having good communication skills. So something that I want to advise you is focus on both. By going to grad school, you certainly get your knowledge, expertise in your field, but also focus on being a good team player. Sometimes our field can be very individualistic, and sometimes that's good. If you want to become a technical expert, you may not need to work in a team environment. You may become an individual contributor, but your opportunities are more limited. If you're a good team player, if you are a good leader, if your communication skills are excellent, then there will be more and more opportunities. So that's something to keep in mind. Another one is business sense. And what I mean by that is, don't be like let's say like a robot who works on something without understanding why you're working on that. Try to understand the organization you're working on. Try to understand the goals of that organization, how that organization works, how they make money, how they grow, and then you'll have a sense of purpose. You'll know why you're doing what you're doing, how you're contributing to that, to the success of the organization, and then you can think about how you can make that organization more successful, and that is also going to open doors for you. Don't be afraid of asking questions. Be always intellectually curious. Never stop learning, especially nowadays. As you know, these days, Google knows everything, right? You can look online for a lot of there is a lot of knowledge available online. So that's not the difficult part these days. You need to learn about how to apply that knowledge and where to obtain that knowledge. That's very important. So, but in any case, never stop learning. Be entrepreneurial. Be proactive. Don't wait for folks to tell you what to do. Take the initiative. And something really, really, really important. That's going to be the last one. The last bullet point in this slide is learn to be multidisciplinary. Aim to be a polymath. If you don't know what a polymath is, you may have heard the term Renaissance man, or well, now we should be more inclusive. It should be Renaissance man or Renaissance woman, and it's somebody who is really good at many different things. Like the ultimate Renaissance man would be Leonardo da Vinci, somebody who was excellent, who was an expert in so many fields, who excels in so many fields. That's my suggestion for you. I mean, not everybody can be Leonardo da Vinci, obviously, but use that as your inspiration, because our industry today and more in the future is going to be multidisciplinary. So now learning about power systems is not enough. You need to learn about telecommunications. You need to learn about power electronics. You need to learn about artificial intelligence. You need to learn about analytics. So yes, we need to be multidisciplinary. So these are some of this is some of my advice based on what I see today in the industry and based on my experience. And I'll share my contact information. If you want to chat one of these days about any of this, I'll be happy to have a quick phone call with you. So now let's go to our agenda. We already went through introductions. Now we'll talk about a few definitions, the scope of resilience, metrics, which is very important, the evaluation of resilience, and some solutions, and also trends and challenges. Something important here is you may have heard the term resilience or resiliency. Both are correct. I guess that is a matter of preference. It's like one of those things like data and data. I guess that sometimes it's a preference of how you want to write it, but both of them are correct. So there is another term that is well known, that is reliability, and sometimes both reliability and resilience tend to be used as synonyms in some cases or interchangeably. But there is a difference, and this is an area, something that is very important. This is an area that is still evolving. So what I'm going to share with you is based on definitions that many folks use, but you may find literature that uses somewhat different definitions, but we'll chat about that in a moment. So when we talk about reliability, and this is from an IEEE dictionary of different standard terms, the definition is, well, the probability that a system will perform its intended functions without failure, within design parameters, under specific operating conditions, and for a specific period of time. Okay, so I think that is pretty clear. Now, when we talk about resilience or resiliency, the definitions that I like are also from IEEE and from FERC, the Federal Energy Regulatory Commission. So the definition, one of the definitions that is, I would say, most accepted in the industry is the ability to withstand and reduce the magnitude and/or duration of disruptive events, which includes the capability to anticipate, absorb, adapt to, and/or rapidly recover from such an event. So a good analogy is you have a pole, and when you talk about resilience, ideally the analogy would be there is a strong wind and the pole bends back and forth, but eventually after the wind, it doesn't break. After the wind, the pole returns to its normal position. So it was able to withstand the problem, and it was able to absorb and to adapt and rapidly recover from such an event. So that would be an analogy. If the pole breaks and we start measuring for how long it was broken and when it was replaced and system service was restored, then we get into reliability. So that's a good intro to what we call the relationship between reliability and resilience. And at a very simplistic level, one way to describe it, going back to the pole, is that reliability is a performance measure. So as I said before, once the pole breaks, we start measuring the performance of that asset. Once eventually the pole is going to be replaced and the event is going to end and service is going to be restored. So it's a performance measure, while resilience is a characteristic of a system. Remember when I mentioned that the pole was bending back and forth, but it was able to survive through the event. So that's a resilient pole. And the one that was broken, that was not resilient, but it's a characteristic of that system or of that asset. Something very important is that in many cases, better reliability results also in better resilience and vice versa, but it is not always the case. So I'll give you one of those examples that is kind of unusual, in which you improve reliability, but not necessarily resilience. So it has happened in California, for instance. You have heard about the wildfires in California, and some of those wildfires may be caused by, for instance, reclosing operations of circuit breakers. Now, those reclosing operations of those circuit breakers are intended to improve reliability, to allow temporary faults to self-extinguish. But so that is a good practice, and it's a practice that is used all over the world. Letting reclosers or letting circuit breakers to reclose, and sometimes when we apply it to distribution, we call that fuse saving. So they can allow temporary faults to self-extinguish. It's a good practice from a reliability point of view. But if there is a tree branch, for instance, touching a line, which that would be, I suppose that is touching the line back and forth due to strong winds, so that would cause a temporary fault. But if we do if there is a reclosing event under those conditions, when the tree branch touches the line, there may be a spark, and that spark, there may be a small arc, and that arc may cause a wildfire, especially if the area is in the area grass is dry and the forest is dry because of, for instance, drought issues, then that may cause a wildfire, and that may cause a big problem in the vicinity of the fault and also in the power system. So that type of issue is a resilience problem. So so you can see in that case, although reliability was improved, resilience was actually affected. So that's something to keep in mind. Okay, another point of view about resilience and reliability is that resilience includes all hazards and all events, including what is called high impact, low probability, or low frequency events that are commonly excluded from reliability calculations. And I'll give you an example. Well, the wildfires example is a good one, but for instance, hurricanes in the Gulf Coast. I live in Houston, Texas, so we, hurricanes unfortunately are common in the Gulf. So when we design a system, either transmission or distribution, we design it within what is called normal operating conditions. So yes, the systems are designed to withstand certain types of weather events, but a hurricane, a Category 5 hurricane, or a tornado, let's see, I think that is an F5 tornado as well. I think that is the maximum category. The winds are so strong that, well, even if we designed a power system to withstand those type of winds, probably there wouldn't be homes in the area to serve. So in designing such a system would be really, really expensive. So it wouldn't make sense to do that. It would be too expensive, rates would be too high, and probably end users wouldn't be willing to pay for such an investment. So that's the reason why when we design a system, we tend to exclude those type of events. When we analyze a system from a reliability point of view, we exclude those type of events that are called major or severe events from our reliability calculations. Now, from a resilience point of view, we should include those type of events in our analysis and in the preparation of the system to withstand those issues. So how do we do that? We'll talk about that in a moment. So we have to look at infrastructure. Infrastructure is going to help to a certain extent, but we also need to look at operations practices. We also need to look at logistics. And when we combine all of those solutions, then we end up minimizing impacts on resilience, but we cannot rely on a single solution. So this is something that is called the Resilience Trapezoid, and this explains a little bit this resilience concept. So let's think about this as a system, and we have a pre-disturbance resilience state. Then there is a disturbance, and this can be a hurricane, it can be an earthquake, it can be a major event, or something that is uncommon, that is usually outside of the realm of, let's see, traditional or common events that are measured by reliability analysis. So there is a disturbance in progress, then performance is degraded, and then there is a restoration of resilience, and then we have a post-restoration state. So one way to measure resilience is to focus on measuring the impact on that, measuring this area, basically, the impact on that resilience trapezoid. Now, remember that I mentioned that you can address resilience by using infrastructure and also operations aspects, okay? So if we focus only on infrastructure, maybe resilience performance is going to be something like this. There's going to be a significant degradation of resilience. If we improve our operations practices, still there is going to be a degradation, but it's not going to be as significant as without addressing that specific aspect. Now, these days, when we when we think about improving resilience, we think about not only foundational aspects, the foundational infrastructure, wires and poles and towers. We also think about using intelligence devices, using real-time monitoring and control, using advanced systems like EMS, ADMS, etc. So in this slide, we show how they can contribute to improving resilience. When we look at the baseline, going back to the previous case, that would be our baseline, right? So if we look at our baseline here as the red line, when we implement infrastructure solutions, basically what we do is to try to make that foundational infrastructure stronger, more robust. And a good example would be we may decide to underground a part of the grid. We may decide to reinforce towers or use poles that are not wood poles. Maybe they're going to be concrete poles, or they may be a polymer poles. We may want to reinforce specific structures, so that there is an improvement in resilience kind of across the board. You can see that with respect to the baseline, there is an improvement across the board. When we use intelligent technologies, for instance, to improve restoration, then in that case, we are not addressing the foundational infrastructure. That doesn't change at all. What we are trying to do is to recover faster from that degraded state. Ideally, what we try to do is to combine both, and that creates a greater improvement in resilience when you combine both type of conventional and intelligent solutions. The next few slides, we'll go through them fairly quick. These are just examples of why resilience is becoming important. And probably I'll just share, instead of going through this slide, this is more for your information, some of the key trends. And many of you may be working with Professor Parvania on aspects such as cybersecurity, so you know that resilience is important from that perspective. We also have the physical aspects of the grid, of course, but I wanted to share another experience with you, a recent experience here in Texas. You know that a few weeks ago, a month ago, we had a major event here in Texas due to climate change. Basically, we had a very uncommon, very cold few days in Texas. And that generated a series of issues with generators in the ERCOT market. They were not available. At some point, I think that around 50% of the capacity in the market was not available, and there was a need for blackouts. It's one of those, let's see, black swan type of events, one of those events that happened, although something similar had happened about 10 years ago. The type of weather that we experienced was something that had not happened in this area for, I think that the last time was something like 70 or 80 years ago. So those events the expectation is that they may become more and more common. So you can see that that's one of the reasons why we are interested in resilience. We want to understand how we can prepare for those events. We may not be able to, going back to our resilience trapezoid, we may not be able to prevent the event from happening, but what we are trying to do is to mitigate the impacts from that event to the extent possible. So that's one example. There are others here, also related with the integration of renewables. As you know, the more renewables we integrate, especially inverter-based renewables, the more inverter-based renewables we integrate, and if at the same time we are retiring conventional synchronous generators, especially coal, there has been a lot of retirement of coal. So basically we are losing inertia in our system. So as you know, inertia is valuable when you're dealing with contingencies. So there have been some events in which it is clear that the integration of inverter-based technologies is not as easy as it sounds. We need to look at so many so many different aspects. Inertia is one of them. So we are focusing on resilience from that point of view too. In this case, it would be events that may be created by the industry itself, because we are evolving. The event in Texas, some people argue that it was a combination of both. Certainly, it was one of these low probability, high impact events, but at the same time, we created the ERCOT market with what is, let's say, considered by some market experts as flaws. And it was kind of a perfect storm, a combination of one of those low probability, high impact events that ended up exploiting one of those market flaws, and that created that major issue. So the point being here that when we look at resilience, those uncommon events that may affect and create significant impacts can be actually created by either Mother Nature, or it may be created by our industry as it evolves. So what is the scope of resilience? So let's talk about that. Let's talk about that for a moment. This is an attempt at summarizing some of the key areas that we want to focus on. So it includes what we call weather hardening. It includes operations, outage management, restoration, physical security, cybersecurity, aging infrastructure, climate change aspects. These days, we need to think about epidemics and pandemics as well, geomagnetic and electromagnetic pulses, and why not? Reliability as well. As I mentioned before, there is a relationship between both resilience and reliability. It's not that reliability is included under resilience, but that there is a relationship between both of them. We already talked about this, some of the different, let's see, the different elements that impact resilience. So we talked about natural hazards. There are also some events that are created by us humans, like cyber attacks, physical attacks. I mentioned before the evolution of the industry. And then we have some of those low probability, high impact type of events like geomagnetic and electromagnetic pulses. There are also some events that are not necessarily technical in nature, like procurement. What happened last year with COVID-19 ended up affecting the economy, ended up affecting, I'm talking about the lockdowns, they ended up affecting the economy, they ended up affecting manufacturers of critical infrastructure, of critical assets. I was talking to a colleague from a utility who was trying to purchase in the middle of the pandemic, when we were kind of in the worst part of the pandemic with the lockdown, etc. He was trying to purchase power transformers, and factories were closed. Vendors were trying to figure out issues with the supply chain. There were delays in deliveries. So that's a good example of those disruptions in supply chain. If we don't have assets, we cannot replace aging infrastructure. We cannot build new infrastructure. So that's an example of an impact on resilience of something that is not necessarily technical. So you can see that the scope of resilience is very broad. Something that is important about resilience is that there are no established metrics. What we have is emerging metrics that are being discussed in the industry. We don't have something similar or equivalent to safety or SAIDI or loss of load probability that are so common in reliability calculations in transmission and distribution systems. We don't have something equivalent that is standardized, that is so well known to measure resilience. We are working on those things. So I'll talk about this slightly. There is a lot of information in the presentation, and I'll share that with you. What I can tell you is that DOE has been working actively in this area. there is a grid modernization laboratory consortium that has developed a framework and has proposed a series of metrics to evaluate resilience. At the same time, also in IEEE, we have the IEEE Distribution Resilience Working Group that is working under the T&D Distribution Committee, T&D Committee. And they also have they have proposed a couple of metrics to measure resilience. And we'll go through them real quick. Going back to the metrics proposed by DOE, DOE has two approaches, something that is called multi-criteria decision analysis-based metrics. And these are more high-level type, more qualitative, not high-level, qualitative type of metrics. So, and they try to answer this question: what is the current state of resilience of an electric system, and what are the options to enhance that resilience over time? Remember, MCDA, they are qualitative. At the same time, you have performance-based metrics. Those are quantitative. And they try to answer this question: how would an investment impact the resilience of a system? So we have two options. We have qualitative metrics and quantitative metrics. Which one should we use? Well, it depends a lot on data, because you'll see some of this data is sometimes difficult to obtain, especially when you look at distribution systems. When you look at transmission, it may be slightly easier, but when you look at distribution, it may be a little bit more difficult. What researchers are trying to do these days is to try to combine both and then come up with something that is perhaps more comprehensive. So this is an example of multi-criteria decision analysis metrics. So there are basically, the intention at the end is to calculate a resilience index. That resilience index looks at 4 different aspects: preparedness, response capabilities, mitigation measures, and recovery mechanisms. Remember, this is the one that is qualitative. You can see that preparedness looks at planning, it looks at awareness. Mitigation measures looks at extreme weather, at utility systems like dispatch centers, etc. Response capabilities looks at internal and external capabilities, and also at something that is called Incident Management and Command Center, which is, this is basically the emergency operations centers that all utilities have. Especially, I'm familiar with the ones that operate in the Gulf. When a hurricane is coming, there is a sort of war room where utilities have access to a variety of information in real time and planning and where they also make decisions about collaborating, requesting support from other utilities, requesting support from FEMA, etc. So that's an important component of response capabilities. And then you have recovery mechanisms. This is more related to the operation of the grid. So this is an evaluation that is qualitative. You can elaborate questionnaires, you can interview folks and operators of the grid, you can conduct surveys, you can look at the inventory, a variety of things, and then you end up developing a resilience index that, as I said, is qualitative. Then you have consequence-based metrics. This is more the world of us engineers. And some of them, you can see that are, they can be calculated based on or using data. Like examples, and here it's important to emphasize that there are two different components or different points of view here. One is to measure the direct consequence of an event, and the other one is to try to measure the indirect consequence of an event. In the direct consequence category, we have metrics such as cumulative customer hours of outages, cumulative customer energy demand not served, average number or percentage of customers experiencing an outage during a specific period of time, etc. And then under the indirect aspects, we have we start getting into the economic side of things. For instance, the monetary impact of an event, for instance, loss of assets and business interruption costs, impact on gross municipal product or gross regional product or gross domestic product if it's a country that is affected. So this is more usually indirect impacts or consequences are more related with economic or regional economic impacts, and direct consequences are more related with impacts on the power system itself. Let me skip this for a moment. So we have talked about definitions, we have talked about metrics. Let's talk about frameworks to evaluate resilience. So I mentioned that there are researchers that are trying to combine MCDA metrics and performance metrics into a single framework, and this illustrates that concept, a single framework that allows you to evaluate resilience and also to identify solutions to improve resilience. There are a variety of frameworks available in the literature. So I have included a few references here that I like you to, I would suggest you explore. I'm not going to go through them in detail. Sandia National Lab, for instance, has developed a framework. In general, DOE has been doing a good amount of work in this area that I encourage you to explore. This is an evaluation of resilience using consequence-based metrics. This presentation is also available online. I liked it very much. It was presented at ISGT last year, and I think that they did a nice job evaluating that resilience trapezoid, and then evaluating how the implementation of a variety of improvement measures could improve resilience. So we talked about metrics, well, definitions, metrics, brief introduction to frameworks. Let's talk about the value of resilience for a moment. Okay, so what do we mean by that? So yes, we improve resilience. Let's suppose that we do that. We are able to measure resilience, the baseline resilience. We are able to measure the new resilience after implementing a variety of solutions, infrastructure solutions, smart solutions, etc. The question is the delta. Okay, so we have a delta, which is the improvement. So can we quantify the value that delta provides? The short answer is yes. There are a variety of evaluation approaches, and this is important because if you work for a utility or a transmission organization, and let's suppose that you want to sell your plan, you say, well, I'm going to be able to improve resilience, and I'm measuring it this way, and I'm able to improve resilience by this amount, by this percentage. So the question would be, so what does that mean for end users? What is the value of that? So these methodologies, there are bottom-up approaches and there are economy-wide approaches. In general, these are econometric type of approaches. They allow you to calculate or to estimate the value of resilience. This is still an evolving area. It's a nice topic for research if you're interested in a Ph.D. topic, for instance, or a master's topic for your work. This would be a nice area. It's still very emerging, but you need to have some skills that are related with econometrics, as I mentioned before. It's a nice area to explore. And this value of resilience is related to this. So again, if you work for a utility, or if you're a consultant and you're advising a utility, and you want to justify investments, and those investments may fall in several different categories, and we'll talk about that in a moment. So you need to think about that value of resilience. How do you justify those investments? In the past, the justification for new investments was related to improving reliability, to improving safety. It was related also to regulatory mandates. A good example would be a regulator, a commission, the Public Services Commission of a state may say, well, we have decided, or we have been requested to establish a renewable portfolio standard. And that renewable portfolio standard is of interest for our society, for our community, and it's going to be now in 2030, 50% of the energy that is procured in this state is going to be now renewable. So that could be a regulatory mandate. There are also, from a utility point of view or a service provider point of view, or transmission, an RTO, a transmission organization, there may be also some strategic projects. Those are projects that may be difficult to justify, but we know that we need them. There is a very good reason. We know that we need them. We know that let's see, they are going to be important for the future of the organization, or they are going to be important for clients, for customers. So that may be a strategic project. And then more recently, we have resilience as another alternative to justify grid investments. And when we look at resilience, what type of projects do we look at? So we need to look at several different aspects. Weather hardening and climate change preparedness would be one of those. And going back to the event in Texas, that event falls investments that would address that, the impacts of that type of event would fall under this category for sure. One of them, if you do a little bit of research on that event, there was a lot of discussion about weatherizing generation facilities. And by that, what they mean is to make sure that they can operate without disruption under, let's see, very cold temperatures. So that would be weatherizing, and in a latitude like Texas, it's certainly related to climate, extreme climate events, because as I mentioned before, this is a type of event that happens once every, let's see, 70 years or so. So that would be one example. Another one would be optimize the system capacity. This is more related with what we call capacity planning, aging infrastructure replacement. That would be a good example in this case would be, for instance, in the downtown areas of large metropolis like New York, for instance, or Chicago, the need for replacing underground cable that may be 100 years old. That could be one example, or poles, overhead poles that may be, let's say, 70, 60 years old. They may still, be around. They may still be part of the existing infrastructure, but their condition may require replacement. Managing assets, managing the life cycle of an asset, investments related with that, with physical and cybersecurity, with very unlikely but high impact events like electromagnetic pulses. Logistics, I mentioned before, logistics, staffing can be a challenge sometimes, even processes. I'll give an example of staffing issues. During the pandemic last year, for instance, you may have heard about sequestration of operators in control centers. And that was done, sequestration in that context means that operators were requested to basically live for a few weeks at the control center and to isolate from the rest of the employees of a company, of a utility or RTO, or independent system operator, because of the risk of contagion. So these operators didn't, for instance, go to their homes for weeks in some cases, because if they got sick, there was nobody basically to replace them. So that would be one example. The interactions or the interdependencies between critical infrastructures like gas and the electric infrastructure, that was also observed in the Texas event. There was a shortage of gas that ended up affecting some of these natural gas generation facilities. Telecommunications is another one. Cybersecurity events would be there is an interdependency between IT, telecom, and the electric grid. Then we have investments that may be related with maintenance, with advanced control, advanced automation, with reliability, outage management, and restoration, with real-time operations, with advanced modeling, planning, and analytics. Analytics is very important these days. It's also an area of growth. We are deploying thousands of sensors in the grid. We are increasing awareness, visibility over the grid, real-time operation, and all of that. But we need to collect that data and process that data. So there has to be some investments on developing those capabilities. I talked about sensors already, intelligent devices, a lot of deployment of automation. We also have advanced protection. That is another area that requires where there has been a lot of investment lately. It's also an area in which that has can have significant benefits from a resilience point of view. And then we have DER integration. So DER integration, as you know, is changing the industry, but at the same time, it's creating impacts that we need to address in many cases through investments. And a good example would be if there is, for instance, a voltage increase or significant voltage fluctuation in a line, or if there is a need to increase hosting capacity in that line for some reason, then an investment could be to reconductor that line. It may be to build a new feeder. It may be to reconfigure the grid to try to mitigate some of those impacts. So those investments can be also included under not only under the planning or reliability benefits category, they could also be included under the resilience benefits category. In this slide, and you can take a look at it in more detail after the presentation, I include some examples of each one of those. In each one of those categories, I include some examples of potential solutions and investments to address that specific category of resilience. So some of the ones that I just mentioned are included there. The next ones, and I think that I'm going to stop in a moment. In the next slides, what I have is some more concrete examples of solutions to improve reliability and resilience. And some of these examples are from all over the world. This first one is from Hong Kong. This is what I call a high reliability, high resilience distribution design. Here in the US, we generally operate distribution systems, distribution feeders. We build them as a mesh. It's a mesh configuration, especially in the cities, but they are operated radially. So that means there is always a normally open point. We don't have closed loops. Generally, that's the case. There are a few exceptions, but those are what I just said, exceptions. We can talk about those. Generally, the majority of feeders are operated radially. In this specific case in Hong Kong, and this is an area with high customer and high load density, and they have high reliability requirements too. So what they decided to do is to build. We have in this case 4 substations that are interconnected between them, and every substation has a closed loop. So you can see that this is a closed loop. This is also a closed loop. Another one here. Another one here, and they are interconnected among each other. Of course, there is a normally open tie between them, but if there is the way they are designed is if there is an issue with one of the sources, this configuration allows the transferring all of the loads from a substation to the remaining substations by opening and closing some of those circuit breakers. This excess that you see here, those are circuit breakers. And these are transformers, of course, and these are just line sections. So the reliability in this case is quite high. I mean, when you go to cities like Hong Kong or Tokyo or Singapore, reliability is really quite high. The next few slides, I'm not going to go through them. They are just for you, for your information. They provide additional examples of solutions to improve resilience. We have microgrids, an example of a microgrid in Chicago, in the Bronzeville area. This was developed by the local utility, by ComEd. We talked about real-time distribution operations. Some of the solutions that are being explored in the industry these days are related with the deployment of distribution PMUs, synchrophaser technology in distribution. And then this one, let me stop here for a moment, and this is probably the last one. Just wanted to show you some examples of products. I mean, real products, sensors. When we talk about sensors that are being deployed in distribution grids, we have advanced fault circuit indicators, we have fault transmitters, we have new intelligent devices that are being deployed at service transformer level. We already talked about synchrophasers being deployed in distribution grids, sensors that allow you to, with a single meter, to measure the output from behind the meter DER, as long as the consumption at a home, and all of this being monitored by utilities. So all of this provides a real-time awareness and visibility over the distribution grid, which has a significant benefit on resilience. I'll stop probably in a moment. The next slides are just basically examples of other technologies. We talked about wildfires. This one discusses wildfires a little bit. Automated fault location is also a technology that is being explored in the industry. The concept of DER readiness, the DER integration is creating plenty of challenges for utilities. The point here is that if we know that it is creating challenges, we should get ready for it. We should be proactive and prepare for it. So this framework discusses that aspect. This is something that utilities like Hawaiian Electric, this is from Hawaiian Electric, one of the utilities with the highest penetration levels of DER in the world, that they are pursuing this concept, especially from the point of view of deploying the infrastructure that is needed, the monitoring, protection, and the switch gear that is needed to operate in a bidirectional power flow world in a distribution grid. Smart inverters is part of that solution. Distributed energy storage is also part of that solution. Grid analytics, also part of that solution. And then we have some emerging technologies like fax devices. Fax devices are established in transmission, but they are still an emerging solution in distribution. It's being explored already by several utilities. And then I'll skip this slide. This is, let's keep in mind climate change. Climate change is real. Despite there is a lot of controversy in the industry, I think that the data supports the fact that that is happening, and we need to prepare for it. There may be a philosophical discussion about or not about the causes of climate change, but the fact is climate change, the data demonstrates that it's real. So the industry in general is preparing for it to address aspects. This slide discuss all of that, and this is the last one. And sorry for going through those last few really quick. As I mentioned before, this is more for your information. The conclusion, I just wanted to close the presentation just reminding you about the fact that this is an evolving area, and many of you are grad students looking for areas to explore, potential Ph.D. dissertation topics. So I would encourage you to explore resilience. There is a lot to do here. Metrics are still not fully, there are so many metrics proposals, but still there is not a lot of clarity yet about what to do in terms of metrics, the evaluation of resilience, frameworks to evaluate resilience, and the relationship between resilience and climate change. So again, I like to encourage you to explore this area, and I'm happy to answer questions and provide advice if needed.